Well, hi again, this is Bob, and I'm over on the bottom of page 430, and we're getting ready to talk about p-values. And I tried to foreshadow a little bit about this topic at the end of my first presentation, or part 1, on 8.2. This is just another way of expressing our answer. There really isn't much new here from when we use this formula here. In fact, we're still going to use this formula. The only thing different is when we get an answer from this formula, we're going to take that answer and we're going to convert it into the actual area it represents. So let's say that we get some value from this, our equation, when we're testing our hypotheses. That value will be changed into an area. Let's say it's a right-tail test, and here we'll have our critical value and normal. Now, either the area, if this represents a critical value of 0.05, we know that there's a cutoff with 0.05 for this would be a right-tail test, and you may or may not recall that for 0.05 that value is 1.65. Well, we know that if we got a z-value less than 1.65, that we would not reject the null hypotheses. But if we got, let's say we got a p-value or a z-value of 1.7 or 1.72, for example. Well, clearly from what we learned in the first part of my presentation on 8.2, since the z-value of 1.72 is bigger than the critical value of 1.65, we would indeed reject the null hypotheses. The only thing new here is we're still going to reject the null hypotheses, but in this on these particular types of problems, we're going to take that, in this case, z.172, and we're going to convert it into an area. And we've done lots of questions like this using our standard normal distribution tables. So instead of giving an answer in terms of a z-value and saying, okay, I'm going to reject, now what we're going to do is change the z-value into a p-value, which is the actual area in the tail, but we would still reject the null hypotheses. It's just a different way of expressing the answer. And if you want to think about it as one more step, that's fine. But we'll explain the reasoning and the ins and outs of this as we go along. Before we do anything, though, I would just like to point out a very important property in case you haven't discovered it for yourself yet. So important I wrote it down and now I can't seem to find where I put it. Oh, okay. I'm going to set up that same situation again. And let's say that we had a right-tailed test at alpha equal 0.05. And we know the cutoff value for that is 1.65. Okay? So, and of course, at alpha, now, so there's the situation. Let's say that we did our equation and we came out with 1.70. Well, right away, we know we're going to reject the null hypotheses because 1.70 is greater than 1.65. Okay? So we're not changing anything in terms of rejecting or not rejecting the null hypotheses. And we know that the cutoff or critical value for the situation where we have an alpha 0.05 on a right-tailed test, we know that situation. The only thing we're going to do different is clearly as the z-value in this case gets bigger, look at what happens to the area in that right tail now. if you go look in the book, as we learned in Chapter 6, for a z-value, let's say the z-value of 1.70 is here. Well, clearly, even more clearly, we can see that it's bigger than 1.65. We're still rejecting, but now we can find out the actual, or they want us to find out the actual area with this test value. And I went ahead and looked it up before. It's 0.0446. And clearly 0.0446 is less than 0.05 in terms of area. So there's two things I'd like you to see here. The first one is the larger, when we're on the right side of the table, the larger the z-value becomes, the less area there is in the tail. In other words, when we had a 1.65 as a z-value, it cut off the graph to where there's 5% in the tail. And now when we have a z-value of 1.70, there's only 0.0446 amount of area in the tail. And that area can be thought of as probability. Now, I'll do one more here. Let's say that we had a z-value of 1.80. Let's say that that was right here. Well, we're still going to reject the null hypotheses. Certainly 1.80 is bigger than 1.65, but the area associated in that right tail with a z-value of 1.80 is 0.0359. And again, we know how to find these areas from Chapter 6. So the stressing point here is the greater the z-value, the smaller the area in the tail. Okay? And of course, that when we get to the left side, we would say the more negative the z-value is, the less area in the tail. But we'll just try to hammer home the main idea here with a couple of good examples and some more theory. But there is absolutely nothing new in this section as far as the math goes, because we learned how to change z-values, we learned how to find a given area associated with a z-value way back in Chapter 6, and now we're on our last Chapter 8. Anyway, what do they mean when they say p-value? And this is the bottom of page 430. They tell us that p-value, or probability value, that's what the p is standing for, is the probability of getting a sample statistic, such as a sample mean, which I just showed, or a more extreme sample statistic in the direction of the alternative hypotheses when the null hypothesis is true. Now, what that means in English is the smaller that p-value, the more probability, basically, that we are correct in our rejection of the null hypotheses. Okay, we know how to reject the null hypotheses, and the p-value tells us, there's another definition or example of it later, but they tell us it's the probability of getting an even more extreme value. Like if we got 170, well, I think the best thing to do is just wait till we get to an example instead of trying to make up some or jump ahead. Let's just use the book's definition right now at the bottom of page 430 for the p-value, and remember that it's based on area, probability of getting a sample statistic or a more extreme sample statistic in the direction of the alternative hypotheses. And when we do the first example, we'll see what that means. Anyway, I'll use their excuse me, their drawing on the top of page 431. This is obviously a right-tailed test, so I'm going to exaggerate it a little bit. This is our critical area here. And here's where they marked off the 5% of that critical area. And of course, here would be our non-critical area. It's all, as you recall that I mentioned several times in these presentations, everything happens in the tail. And I know that's not the best representative drawing, but I need more space for this, my computer here. Anyway, we have an area of 0.05. Now they have a sample mean. They've left this in raw material here, so to speak. And so I'm not putting in the values that the z-values, even though I always stress the drawing. Here we have an area, is what they're showing here, at our critical value. That's an area of 0.05. And actually we know that the z-value there is 1.65 because we've seen it before, okay? But anyway, then they show us another area. This is the way they're doing it. And that area is 0.0356. Okay, now obviously that represents that area. I'll just go ahead for simplicity's sake and say there is our critical value of 1.65, which we know associates with a alpha of 0.05 on a right-tailed test. Notice that, now check out or compare 0.05 versus 0.03. Keep losing this darn pin here. Okay, clearly whatever the z-value associated with 0.0356 is, it's got to be bigger than 1.65. And recall what I just said, as we get larger z-values, the amount of area in that right tail gets smaller and smaller and smaller. Okay, so in this case, if somebody asked, well, what's the p-value there? You would say, well, the p-value is equal to 0.0356. And if somebody set up a question and said, well, I want you to tell me whether we should reject the null hypotheses for a given situation at alpha equals 0.05. Well, clearly, if we got a value that was z-value bigger than 1.65, its area would correspond to 0.0356, and clearly we would still reject the null hypotheses because 0.0356 is further into the tail, and obviously as we get further into the tail, the area in the tail gets smaller. And then finally, the last thing they do is they even cut that tail up more, and they show where there's only 1% of the area of the curve in the tail. In other words, that would leave the rest of it to be 99%. Okay, and if, remember, when we say alpha equals 0.05, we're talking about an area in the tail. If we get a p-value of 0.01, we would clearly reject the null hypotheses because 0.01 is less than 0.05. Okay, well, I think the best thing to do, let's read these rules, but it always seems to make more sense when we do one of the book's examples. But they've got two rules on page 431. If the p-value is less than or equal to alpha, so I'll write it this way, if p-value to alpha, we are going to reject, just like before. The only thing before, we didn't change the z-value into a p-value, and now they're giving us an alternative method. And if the p-value like this, my pen is starting to act up, but if the p-value is greater than alpha, if p-value, I should have written alpha up here. You know what, this is so frustrating sometimes when my pen gives out. I could just read this, but I want to do it as best I can. If our p-value is less than or equal to our alpha, we reject null hypotheses. Okay, and my pen's now working again. If p-value is greater than alpha, remember a p-value is an area and alpha is an area, then we don't reject. Null hypotheses. Okay. And then, of course, after that, we know where we can find out, in case you have forgotten, we're going to get a z-value, and instead of directly or not reject the whole null hypotheses, even though we would know at that time whether we were going to reject it or not, we're going to take the z-value and convert it into a p-value. And they tell us a little later that many times a researcher or statistician will just report the p-value and let whoever is looking at the study make up their own mind with regard to how good the study or results are. Okay, but you may recall, if you don't remember how to find a given area associated with a z-value, and it's going to be this type of situation here. Let's say this represents our alpha of 0.05, which would be 1.65. Let's say you got a z-value of 1.92, which would represent this area. You should recall how to go into the z-tables and find out that area there. Recall what you would do is you would find the area to the left of 1.92 and subtract it from 1. Okay, and then that would be your p-value. Okay, as always, I feel this getting very wordy, but at the bottom of page 431, they have a procedure table. This is a little different. I'll put the new stuff. Step 2 is we compute the test value. In this case, it will be find the z-value. That's just like before. And then step 3 says change the z-value to a p-value. And then, of course, step 4 says make the decision as to reject or not, and the last step is to summarize the results. Okay, well, if you can understand question 8.6, there's 2 really good examples here that I'm going to work. And even though we don't have to, I'm going to draw everything out because I think that helps us. So this is the cost of college tuition. It's the exact same type of question we had before. You could correctly work this question without using the p-value, but it's something the book wants us to learn, and we're going to see it with other tests also. Anyway, the researcher wants to test the claim that the average cost of tuition, this is example 8.6 by the way, the average on page 432, okay, we're going to test the claim that the average cost of tuition and fees at a 4-year public college is greater than $5,700. Well, right away, we know the null hypotheses would be it's equal to 5,700. And in this case, remember, we're claiming that it's greater, so our claim will go with the alternative hypotheses. This whole claim thing I've mentioned is used in this book, but I prefer to just reject or not reject when I'm summarizing. But I will continue to follow the book's procedure. Anyway, the rest of the information I'll go ahead and put on the top of the next page there, and you can certainly follow along. The population standard deviation is $659, and a sample of 36 4-year public colleges was consulted or taken. Now, we want to test this at alpha equals 0.05. Now, I'm going to do everything 2 ways, but then it really boils down to 1, as you'll see. The way what we're really doing here, as we saw before, this is a right-tailed test. at alpha equals 0.05. This is about what that looks like. And hoping that when I do this little extra work, it will make it clearer. Now, you can see what happens. Or from our previous part 1, we learned by just going back to section 8.1 that the critical z-value for this, in other words, remember this is non-critical and this is our critical area, and our critical z-value, if you will, is 1.65, although the book doesn't mention it, but that's what it is. Okay, then, so the 1.65 represents an area of 5% in that tail. Now, when they do the z-value, you can follow their logic and their ciphering there. They end up with 2.28. Clearly, from what we know already, 2.28 is larger than 1.65. We are definitely going to reject the null hypotheses. Nothing new here, move on. Well, there is something different though. It's not new. Instead of reaching our conclusion by comparing the z-values, what they want us to do is find this little area here that 2.28 represents further into the tail, and they have found that area to be 0.0113. You know how to do that. Okay? So now what they want us to do is they want us to compare 0.05 versus 0.0113. Well, clearly 0.0113 is less than 0.05. We're much further into the tail. We already knew that we're going to reject the null hypotheses, but now we can tell the actual p-value, this amount of area here, and this is really important because they tell us that that amount of area represents the probability of getting a value larger than 2.28. So we're feeling pretty confident with our answer here and our rejection of the null hypotheses. Okay, so it turns out that the p-value actually stresses or gives us the area, and that area can be thought of as a probability. It seems like there's one more thing I need to mention here. Well, I think you can see it. Okay, so on this problem, they finish off by saying, well, what if we had originally set alpha at 0.01? Well, if they'd originally set alpha at 0.01, then we would not have rejected the null hypotheses because 0.0113 is bigger than 0.01. Okay, so that is how they finish off at the bottom of step 5 there. Okay, so I've one more thing, and then we'll see if we can summarize with a little bit of theory here. But I want to just focus as best I can on working the questions. And here is example 8.7 at the bottom of page 432. Now, remember, you don't actually have to find the z-values for this. We're doing everything by area, and you're welcome to do that, but I always stress doing a drawing, and I'm throwing in the z-values here to sort of hammer home the idea that what we're doing now is like we just did in the first part of 8.2. Anyway, this is about wind speed, and I like the fact that they use the word claim here. And the researcher claims that the average wind speed in the city is 8 miles per hour. It's always easier when they use the term claim. Okay, and now notice that the researcher didn't say he felt it was greater than or less than. He just felt it, or she just felt it was 8 miles an hour. Okay, and then they say a sample of 32 days had an average wind speed of 8.2 miles per hour, and they give us a standard deviation. Is there enough information to reject the claim? Clearly, this is a two-tailed test. So our alternative, because they didn't tell us if it claimed that it was greater or less, just that it's equal to. So we don't know how good that claim is, or that null hypothesis is. And what I'm trying to stress here is, since they didn't say that it was believed that the wind speed is greater or the wind speed is less, that's what makes it a two-tailed test. And of course, our alternative hypotheses would be that the wind speed is not greater than or equal to 8 miles per hour. Okay, we know that the standard deviation is 0.6 miles per hour. And we know that we took a sample of 32 days. Okay, and then the last thing that we're going to use, or we need that the 32 sample over 32 days was taken, and the average sample mean in this case was 8.2. Well, 8.2 is definitely bigger than 8, but we don't know if it's significantly or statistically bigger than 8. So that's what we're going to have to use our z-values and t-tables for. Or not t-tables, but p-tables. Okay, and notice that our alpha is 0.05. So even though this is not fully necessary, but to help understand what we've done before, that would put 95% of the graph in the non-critical region, and each one of the tails would have critical value, you may recall, of 1.96 and negative 1.96. Now, the reason I'm showing this also is to stress the fact that our area, our alpha, is in two tails. Okay, so that's our area of doubt. And it turns out when we have a two-tailed test that we have to do something with the p-value that we get. So here's what they do. They take all that information and they figure out, I'll leave this for you to follow their calculation, they get a z-value of 1.89. Okay, clearly already we know that 1.89 would be maybe right here. Clearly, we should already know that we're not going to reject the null hypotheses, because 1.89 is not bigger than 1.96. Okay, so if that was the only thing they ask us to do, we would be done and we're moving on. But what they want us to do is convert 1.89 into a p-value. So that's a whole separate problem that we've done plenty of. We take 1.89, and in our table it would give us all this area to the left of 1.89, and then we would subtract that from 1, and they would get 0.0294. Now, don't make the mistake of thinking that we're done because 0.0294 is less than 0.05. Whenever we're dealing with a two-tailed test like we are now, again, we already know that we're not going to reject the null hypotheses, but the book reminds us or tells us that whenever we're dealing with a two-tailed test, that what we get for the p-value must be doubled to account for the other tail in its area. So if you notice, the next thing they do is to take 2 times 0.0294, and they end up with 0.0588. And you can refer to their drawing there. Clearly now 0.0588 as an area is greater than 0.05 as an area. And both of these can be thought of as alpha because they're both areas. So again, we don't reject in this case. We already knew that we weren't going to reject based on the z-values, but now we have the actual areas involved. And again, take a look at the figure 818 there to see what's really going on. Now, if you notice, they at no time gave any z-values on that question there. What they did is they just set out the critical areas and the non-critical area. But I used the z-values to, again, reinforce the idea of the, as the larger the z-values, that the tails get smaller, and to also remind us about the alphas. Okay, well, to summarize everything, or they've got a decision rule below that. They tell us that, I think we've already mentioned this once before. I may have gotten a little bit ahead of myself, but I'll just read it instead of writing it this time. If the p-value is less than or equal to alpha, reject. If the p-value is greater than alpha, don't reject. Okay, and then there's finally, it's one last thing to say there, or well, actually there's a couple of things that we need to say. They remind us that on some statistical tests, they won't even bother giving a z-value. What they'll just do is they'll give you the results, and then they'll say there was a p-value of 0.026, or 0.26. And what that really means is the amount of area in a tail or tails. Okay, and that's what they're one of the things that they're trying to tell us there. And the other thing is, I'll give you a situation here. Let's say that you set up a test and you decide that you want your alpha to be 0.01. Okay, and then you go through with your test and you get a z-value. And let's say that that z-value becomes like 0.0126. And you go, shoot, I was really hoping that I could reject this null hypothesis on this experiment. And then you go, oh, wait a minute, what I'll do is I'll go back and change my original alpha to 0.05. Then I can reject because I had a 0.0126 p-value. Well, that's a no-no. We're not supposed to do that. The p-value that we originally choose is the one that we should finish off on, and that's what they're trying to tell us at the bottom of 433. Finally, and I'm just going to read this, but they give us some guidelines with regard to our p-values. Okay, and there are three of them. The first one is, if our p-value, I won't write the whole thing, but if it's less than or equal to 0.01, they tell us to reject the null hypotheses, and the difference is highly significant. And then they tell us if the p-value lies between 0.01 and less than 0.05, this is on the top of page 434, by the way, then they tell us that we're to reject the null hypotheses, and instead of the difference being highly significant, now it's just significant. And then they tell us if we get a p-value that's greater than I'll write it differently. They tell us if we get a p-value between 0.05 and 0.10 that we're supposed to consider the consequences of a type 1 error before rejecting the null hypotheses. In other words, we would have a 5 to 10% chance of making a type 1 error, which is when we reject the null hypotheses and it's really true. And then the last thing, if we get a p-value that's greater than 0.10, then they tell us to do not reject the null hypotheses. The difference is not significant. Okay. Anyway, I believe my examples and definitions and illustrations here should help you do a few questions. And you will notice also that they have given you in the homework, they've asked you to change a few of the, trying to find the place here. They'll ask you to do a few P questions, and in some of the questions, they won't give you a level of significance. They will ask you to go back and interpret this chart on the top of 434 and come to your own conclusion. But it's, I know the question that I wanted to point out was the homework question 15, where they give us some practice on looking up p-values and whether we reject or not. So that'll be good practice for the rest of the p-value questions. Okay, I'll be back shortly with 8.3, which is pretty much the same thing that we've just done here, except we're going to be moving on to the t-test for a mean. Okay, I'll be back shortly. Thank you.